Welcome to the next video in the Chapter 5 material where we're taking a look at the stereochemistry of organic molecules, which again is a look at the three-dimensional shape of organic molecules as related to the concept of chirality. We introduced the concept of chirality as non-superimposable mirror images and how we can have a non-superimposable mirror image molecule on the case where we have something called a stereogenic center. That is 4 different substituents on an sp3 carbon. So here's a molecule that shows an example of a stereogenic center. We talked in the last video about that in some depth. What I want to look at in this particular video is what the influence is of having more than one stereogenic center in a molecule. And so here's a group of molecules that have more than one stereogenic center. So we've got a cyclohexane rings here where we've got an OH group and a CH3 group. And at each of those positions, where each of those carbon atoms is defined as a stereogenic center, each has 4 different substituents on it. So I'll pick one of these, just that blue one right there, then I'll make a dot at that particular carbon atom. If we look at it in some depth, it's got 4 different substituents. It's got the OH group on it. It's got, to the top, to the right, a CH2 group, and down at the bottom it's got a CH group with a CH3 on it and another CH2 in the background, and of course there's a hydrogen atom on there, which we haven't explicitly drawn in this instance here. Okay, so what's the influence of having these different substituents on these 2 different and there's 2 stereogenic centers. The carbon atom down below that has the methyl group on it is also a stereogenic center. There's 4 different substituents on it. And you can kind of take a look at that. If you don't see it from this drawing, you can make a model of these and follow along a little bit. You might find that a bit useful at some point as well too, to make a model of these and kind of play along as what we're taking a look at here. And so now what we want to take a look at is what's the stereochemical relationship of these molecules. So if you look at the 2 molecules that are at the top, if I draw a line down the center here, you see that those 2 molecules at the top are enantiomers of each other. They're mirror image related, but they're not superimposable on top of each other at all. So for example, if I pick up the molecule on the left and I pick it up and I carry it over and I rotate it around and I set it down on top of the molecule on the right, you see that the methyl groups and the OH groups don't line up. And if I flip them over, things don't line up. And if you don't see it on the drawing, I'd say make the model of these and play around with the models. You should be able to convince yourself quite quickly that these 2 molecules are enantiomers of each other. They're non-superimposable mirror image. And so we also see a similar relationship between these molecules at the bottom of this particular drawing as well. So again, I draw a mirror plane or a plane down the center there, and I can look to see what's on, if the 2 molecules are mirror images of each other, and indeed they are. They're mirror images of each other, they're non-superimposable mirror images, and so they're enantiomers of each other. But now, what about the relationship between the molecules on the top and on the bottom? So if I draw a blue line there, for example, what's the relationship of the molecules above the blue line and below the blue line? Well, the molecule, for example, that are above the blue line, their only difference between those and the molecules below the blue line is the so-called what we call the configuration around one stereogenic center. That is, for example, if we go from the pair above the blue line to the pair below the blue line, the only difference is that the methyl groups are pointing down instead of pointing up. So that configuration around those stereogenic centers is different than the ones above. Now, if I look at a molecule above that blue line versus a molecule below the blue line, those molecules are not mirror image related at all. They're not mirror image related to each other at all. And let me show you this. So what I'll do here is I'll take 2 of these molecules and just compare them side by side. I'll take this molecule that's above and to the left of the blue line. So I'll take this one here. I'll just label it as 1. And I'll take this other molecule that's in the bottom right quadrant here, 2, and I'll just compare them side by side to each other. So you can see that they're not mirror image related to each other, but they are in fact related only by the only difference is the configuration of one of the carbon atoms. And so there's those 2 molecules compared side by side. They're not mirror images of each other. In one case, the CH3 is pointing up, the other CH3 is pointing down. So they're not mirror image related to each other, but the only difference is that they've got this one configuration that's different around that one single stereogenic center. So that means that these molecules are what we call diastereoisomers. Diastereoisomers is what those molecules are. And so they're not mirror image related. So the molecules are different from each other. So we said when we introduced RNS, and we'll talk a little bit more about this, but we said that the two enantiomers are completely indistinguishable from each other. So two enantiomers are completely identical with respect to each. All of their chemical and physical properties are identical. Their melting point is the same, the boiling point is the same, index of refraction. All of the things that we can measure in a pair of enantiomers are identical. We can't distinguish them by any physical or chemical property. And so the two molecules above the blue line are indistinguishable from each other because they're enantiomers of each other. But the molecules above the blue line and below the blue line, these sets of molecules that are diastereomeric with respect to each other, they are different from each other in every measurable chemical way. So for example, these two molecules that we've drawn side by side here, all of their chemical and physical properties will be different. They would expect to have different melting points, different boiling points, a different index of refraction. They would act different in chromatography. You can separate them on a column or on a TLC plate. All of their measurable chemical and physical differences should be, in theory, different from each other. And so maybe one of the concepts to imagine this, for example, with this set of molecules, is that it's like having two sets of twins. And so you've got a set of boy twins and a set of girl twins. It's difficult to tell the girls from each other, and it's difficult to tell the boys from each other, but it's very easy to tell the boys from the girls. And so that's an analogy to think about, or to use to sort of imagine these molecules here. Okay, so let's move on, and we'll take a look at other examples of these kinds of molecules with more than one stereogenic center. Let's imagine what we'd observe if we switched out those methyl groups for another OH group. So again, here we look at another set of 4 molecules that we can draw in this instance where we've got OH groups instead of a methyl group, but the same kind of idea. We can line them up and we can see that we get pairs of molecules. And again, here I can draw just a line down the center of these two molecules that we would pretend is a mirror. We've got a molecule on the left, a molecule on the right, and we can see that those molecules are mirror images of each other. The two OHs are above, the two OHs are below. And again, if you don't see it on the drawing, I'd say make the model of these, and you should be able to see it. If you make the model correctly, you should be able to see exactly what we're looking at here right away. And so again, those molecules on the top above the blue line are non-superimposable mirror images of each other. They exist as a pair of enantiomers. All of their chemical and physical properties would be the same. We wouldn't be able to distinguish them from each other. And now we can see that they're also diastereoisomers of the molecules that are below the blue line. The only difference between the molecules above the blue line and below the blue line is the fact that the configuration of one of the stereogenic centers is different. So the two OHs are pointing up on the bottom case. And again, we can see that the molecules on the bottom, if I draw a red line down the center between those molecules on the bottom are in fact mirror images of each other. They're mirror images of each other. And if we look at what we observe there, though, the problem with those ones on the bottom is that, in fact, they're completely superimposable on each other. I can take the molecule that's in the bottom left quadrant, I can lift it up, I can rotate it around 180 degrees, and I can set it right down on top of the molecule in the bottom right quadrant, and they're completely superimposable on each other. So molecules that are superimposable mirror images, they're not chiral molecules. These are not chiral objects. Any object that has a superimposable mirror image is not a chiral object. So these molecules are not chiral. They don't display any of the things that we would associate with chirality, which we'll talk about in another video. So these are achiral molecules, even though they've got stereogenic centers, right? Our very definition of a stereogenic center is a carbon atom with 4 different substituents on it. And so these molecules, the carbons we're labeling in green, are carbon atoms that are stereogenic centers, 4 different substituents. They've got an OH group, a CH2 group, a CH with an OH on the bottom, and a hydrogen atom, which we haven't drawn but is pointing back away from us there. So those are a very definition of stereogenic centers. There's more than one of them, but the result of the way those stereogenic centers are arranged is that these molecules have an internal plane of symmetry. An internal plane of symmetry is what we describe that as. An internal plane of symmetry, so there's a line down the center of the molecule that is plane of symmetry. What you see on one above or below or to the left or to the right of that internal plane is identical. And so if you imagine yourself walking down that purple line that I've drawn down the center of that molecule, and as you're walking down that purple line, you look to the left, you look to the right, you see the same thing on both sides. That's an internal plane of symmetry. I see an OH and an OH sticking up. I see a CH2 and a CH2, and then it's down the center of that carbon-carbon bond. Identical things on both sides. We've got a specific name for what we call these kinds of molecules. We call these meso. So we call these mesomolecules. These are achiral objects that have more than one stereogenic center, and so they fit into a kind of a special category all on their own. And in part, that's why I dislike the term that the textbook uses, which is chirality center, because not every carbon with 4 different substituents is generating a chiral object, and we see examples of that below that blue line. And so this is a very special class of these kind of molecules, and so we just kind of keep in mind of them. So now what I want to show you next is that this isn't just a property of molecules that are part of a cyclohexane ring. This can also apply to acyclic molecules. So in fact, what we have here in the next screen is a set of acyclic molecules with more than one stereogenic center. Again, 2 stereogenic centers in each of the molecule, just like we had with the cyclohexane rings. So we've got, again, 4 different substituents on an sp3 carbon. So for example, we've got a carbon with an OH on it, a CH2, a CH3, and of course the hydrogen atom pointing into the back of the plane of the screen, which I haven't drawn explicitly on these molecules. We can do exactly the same kind of analysis here. Look, we can draw a red line down the center of these molecules. And we can draw a red line down the center of these molecules, and I got to turn that into an OH into a bromine in order to make that the right just to get that to the right configuration, I have to rearrange the bromine and the oxygen. So the ones on the bottom, of course, you can draw a line, red line down the center. We've got those 2 molecules are mirror images of each other. So those red lines, if we think of them as a mirror, we see things that are close, and things that are far, far. So the molecules that are, again, we can draw a blue line down the center of the screen. And the objects that are above that blue line, those 2 molecules that are on either side of the red line are enantiomers with respect to each other. The objects below the blue line are enantiomers with respect to each other across that red line. Again, all the things we said about enantiomers, all their chemical and physical properties are identical above that blue line, below the blue line. But the molecules that are above and below the blue line are diastereoisomers with respect to each other. So the molecules above the blue line would have different chemical and physical properties from the molecules below the blue line, different melting point, different boiling point, different index of refraction. You can separate them by chromatography, all of those kinds of things that we talk about being able to do. And so that applies, so even though they're not as part of a cyclohexane ring, this concept of diastereoisomers applies to these as well. What we want to look at next to see is if we can see the same kind of thing in an acyclic molecule as we saw in the cyclic molecules, where we have more than one stereogenic center. Can we get molecules that have an internal plane of symmetry, and are they meso? Okay, so here's another set of molecules, similar to what we looked at with the cyclohexane rings. Again, I can draw a line down the center of each of these molecules, a red line down the center, and what we observe on either side of that red line, those objects are mirror images of each other. They're mirror images of each other. And above that, we'll draw that blue line in again. Here and above that blue line, we can see those 2 molecules that are above the blue line are mirror images with respect to each other. They're non-superimposable mirror images. They're enantiomers of each other. I can pick up the molecule that's in the top left quadrant. I can pick it up, I can carry it over, and I can set it down on top of the molecule that's on the top right quadrant, and it doesn't match up at all. The OHs are pointing different directions. And if you can't see it from the drawing, make the models of these, and you should see that there's nothing you can do without breaking a bond that would make these superimposable. So those are enantiomers with respect to each other. And of course, above the blue line and below the blue line, those molecules are diastereoisomers with respect to each other. The only difference between those molecules is the configuration around a single carbon atom. We've got OHs going back in the instance, one OH going back and one going OH forward. Above the blue line and below the blue line, both OHs are sticking out towards us on the screen. And now again, of course, the red line shows that they're mirror images of each other. But now hopefully we can see that those are completely superimposable mirror images. I can pick up the molecule in the bottom left quadrant, carry it up, pick it up, carry it over, and drop it right down on top of the molecule in the bottom right quadrant, and they're completely line up with respect to each other. They're completely superimposable. Again, these are also meso compounds. These are meso compounds. They're achiral with respect to each other. They are just achiral objects. They don't do any of the things that we associate with chirality. Meso compounds, even though they've got stereogenic centers. Each one of them has a sp3 hybridized carbon with 4 different substituents on it. So those the concept of diastereoisomers is a central one to organic chemistry, and an important one for being able to understand the 3-dimensional shapes of molecules. As well as that meso concept is also a very important one, because not every molecule that's got stereogenic centers can display the properties of chirality. And so that's an important thing that we take a look at as we sort of examine the 3-dimensional shapes of molecules. And more importantly, the fact that the diastereoisomers have different chemical and physical properties with respect to each other. That's a pretty key and important concept in organic chemistry that we use to kind of explain a lot of behaviors in terms of how these molecules will behave. So for now, we'll leave it at that with this particular video, and the next set of videos that we pick up will take a look at something that we call optical activity.